We've had quite a few good talks today, and it's been pretty exciting. Especially the last two talks are going to make my life very easy. So they've been very comprehensive and I think they have generated quite a bit of interest in functional programming. So anyway, thanks for having me, and thanks for giving me this opportunity to talk about this one topic that I've been really passionate about for the last 5-6 years. I've been doing some research on it. I call it a secret weapon because it's actually like accessible to all of us right now, but most of us don't really know how to use it or what it even is. But if you're able to leverage on metaprogramming, I think, at least personally, my programming skills went to just leveled up. I was able to do a lot more, which I could not have imagined before. So the objective is for me to try and get you an introduction into this pretty large field, and hopefully the interest will keep you going, and you will do your own research and go into this field as well. So, well, let's get into it. Functional metaprogramming. So those are two really large words, enough to make most people yawn. But let's break down the words. So you already know what functional is. Metaprogramming. So what is metaprogramming? Anyone knows? Any hands for metaprogramming? Okay, so all right, let's break it down into two. So we have meta and programming. So what is meta? So this is a simple formula. Meta x is simply x about x. You can talk in terms of some examples. So we have metadata, which is data about data. So for example, if you take a photo, you have a JPEG file. The JPEG file is the data, but you may have aperture speed or aperture size and the shutter speed of the camera that was taking the photo, and that becomes the metadata. Or if you have a Word document, the content is the data, and the author name and the created time is the metadata. So it's actually data that describes the data. So similarly, metaphysics, it's like if physics is a study of nature, then metaphysics is the study of the nature of nature. So it's like one level higher again. Meta joke, jokes about jokes, jokes which make fun of jokes, the similarity between various patterns in jokes. And the central piece of our talk, metaprogramming, is just programs that actually work on top of other programs. And why is this interesting to me? So basically, metaprogramming is a technique where you can write a program that actually reads, generates, analyzes, transforms other programs. That other program might actually be its own self. And if you really think about it, this actually gives us a lot of benefits. So you may be, for example, be able to write a very small program that can then generate very long programs. So you spend lesser time typing out code. You also get less bored in the process because it's more interesting. But most importantly, you're also able to handle new situations which you haven't programmed in directly without recompiling. So the program is sort of adaptive towards what the environment needs. So this is the reason why metaprogramming is particularly useful to AI researchers, as the program is able to learn and evolve. All right, so we've already gone through pure functions, but the reason this talk is called functional metaprogramming is because you can actually do metaprogramming with also imperative style, but with functional programming, metaprogramming actually becomes very easy to the point that if you just look at the next few slides, you may be able to go home tonight and actually write out a quick metaprogram. So as you know, we've already gone through pure functions. The two important points there are they always return the same value for the same set of arguments, and the other important thing is they don't produce any side effects. The cool thing about pure functions is that they can be very easily visualized as trees. This is a very important aspect. The reason for this is because a tree is a simple data structure. You probably studied tree data structures in your data structures course in university. Anyone who has studied trees? on how to browse trees. So we all know what trees are. We all know how to navigate trees. So if you're able to represent your entire program as like one tree, then you can go and modify the code of the program using very simple code. And you can also generate more code by simply generating those trees and then having a simple interpreter at the end, which won't take more than 100 lines of code and actually evaluating the tree. So that's what we're going to see over here. So here's a very simple add function. Takes in two parameters, a and b, and gives you a plus b. So in this case, this is the simplest tree you can come up with. There is a operator at the root. The operator is almost like a function in this case. So there are two nodes left and right, both of which the parameters a and parameters b. So let's make this a bit more complicated. So now we have a arithmetic function. So this is roughly f of x is equal to, f of a comma b is equal to 2a plus 5b minus 7. So how do we represent this as a tree? So let's start with the smallest, innermost layer. So it's 2 times a. So that's multiplication, 2 times parameter a. And then we have 5 times b. That's multiplication, 5 times parameter b. And then we combine the first two terms. So that comes over here. So this plus combines the result of the first expression and the result of the second expression, right? And then finally, we have a subtraction operator, and then we hardcode the value 7 over here. So this tree represents that entire program over there. Of course, for you to write any usable programs, you need to be able to represent conditionals. So a conditional is, so far we've seen binary operators, which is like plus or multiply and all. They have a left side and a right side because they only have 2 operands. A conditional has 3 operands. You have a conditional check, like the Boolean expression, and what to do if this thing is true and what to do if this thing is false. So in this case, we again have a very simple function. Divisibility is divisible by, it checks if a is divisible by b, and if so, it returns true, otherwise false. And of course, this can actually be simplified by removing everything here and just keeping this, but for the sake of this discussion and to like keep this slide a bit simple, I just like expanded it a bit more so it's easier to see. So again, the condition over here is on this side. So first we check, we first create a tree for a modulo b, and then we check, we have a Boolean equal to operator, and we check its equal to, we check its equality to 0. If this is true, then we return true. If that is false, then we return false. So, has anyone here done Lisp? Okay, so we have a couple of Lisp programmers. So this must be very obvious to you guys because this is the basis of all of Lisp. But for the rest of us mere mortals, this tree visualization actually is it makes metaprogramming actually very, very easy. Alright, so the next part. So we have arithmetic covered, we have conditionals covered. The next most important thing are function calls. So here we're combining those two functions which we had just declared to check if the result of the arithmetic function is actually going to be even. So here we just call the function with a and b. We apply that result into is divisible by and use the second parameter as 2. And then if it's true, otherwise it's false. So if you look at it, here is the function call. It's just a simple note that says call this function. There's a parameter a, parameter b. Divisibility call. Again, the second parameter over here is 2. And then we have, this is the conditional, and it returns a true or false. So the interesting thing about this particular thing is the last two trees were fully self-sufficient. Like all the information, if you were to give that tree to somebody else, they'll be able to understand your program very well. But in this case, there are 2 external references. One of them is this function, the other is this function. So what we can do is actually replace those 2 functions with the trees we had constructed in the previous 2 slides. So we basically can expand this tree into something larger. So exact same tree, but the function calls have actually been replaced with the trees from the previous 2 slides. So Why is this important? Why are we trying to expand the tree? What I want to show here is that any program, after all its function calls and everything, can be expanded into one tree data structure. This is important because only if you have a data structure can you write code to modify the data structure. So you got to be able to bring everything down to one tree. So that's what we're doing here. It's just a very simple expansion. So just like you can expand things, you can also compact things. So in this case, let's go back like 3 slides. We have like this arithmetic tree which we came up with. 2a plus 5b minus 7. Assuming we know that the value of a over here is 5, we can plug in 5 over here, and at this point we will notice that all of these are constants, and hence, due to referential transparency which was explained in the previous talk, this whole thing can actually be replaced with the value 10. So that we just have 10 over here. Similarly, the rest of the tree remains the same at this point. That part has been simplified. So now we know that now we apply b is equal to 10 so we have 5 times 10. So we're able to replace the greens with a single node which is 50. Which now, if you look at this tree, there are no more variables left. So you can compact it and it simply becomes 53. So this is the process by which you actually if your tree represents code, how do you run that code? It's basically the process of interpretation. So you just recursively keep going from bottom, keep simplifying wherever you can simplify. As long as there are no variables left, you'll be able to compress it down to one ultimate value. And that is so that program which you're writing to actually parse that tree and arrive at an eventual value, that is actually a metaprogram. Alright, so this is just basic theory. I wanted to show you that if you are able to represent your code as, how do you represent your code as trees? That's what the last few slides were about. Now, what can you do if you're able to represent your code as trees? So this is where things get interesting. I'm going to show you some real examples which we actually have running in our production at Chaldal. So why is it a secret weapon? What does it enable us to do that regular programming does not allow us to do? So this is the first example. So this is our backend, it's written in F#, and of course we have a front end as well. So we have complex pricing and availability algorithms for various items. Of course, this is not complex, this is the simplest line I took out of there. But we also want our website to be really fast. So if we have complex logic for every product, it's going to be very, very hard to bring that logic to the front end and make the front end very responsive. The only way to do that is to then maintain that logic in 2 different places because they're running on different platforms. So what we ended up doing is we were able to visualize this particular pure function as a tree, and we were then able to write a metaprogram that goes through the tree and emits equal in JavaScript out. So our API, when it actually brings a product or when it loads a shopping cart, it not only returns just the data, it also returns some logic sometimes. And this is essentially made possible with a little bit of metaprogramming. So if you notice, this is purely generated from this. So this is one of the reasons why if you go through our website, once it loads up, everything just transitions very, very smoothly because all the logic gets pushed from the backend to the front end. Here's another example. So we also use this to auto-generate some user interfaces. So these are some screenshots from our admin panel. So how many people here write admin panels? Right. How boring are these admin panels to write? Okay, so honestly, that's what drove me to get into metaprogramming, because the problem with doing these admin panels is that everything is roughly the same, but you can't copy paste it. You have to copy paste it and you have to modify things here and there, right? And it's just some brain dead activity which you end up doing after a while, and it really makes you question your choice in careers at some point. So what do you do? So one of the things we did is we changed the way we represent our. So we have this we have a concept of Chaldal delivery. Like one of the entities is a delivery, right? So a delivery can have many functions that can be applied on top of it. So for example, if a customer decides to like reject the delivery, you basically call a function, but that function can't be called if the delivery is not yet dispatched. So what we're able to do with a bit of metaprogramming is, given the current state of the delivery, we're able to go through the code tree and figure out what are the valid functions that can actually be called on that particular state of delivery, which don't result in an error. So with that, we're able to filter out the list of applicable actions, and hence we're able to build out a user interface automatically. So we have about like 30 to 40 screens that we didn't have to write code for. We're also able to figure out the parameters in these functions, and we're able to generate like automatic form fields like this. So this is a very, very powerful use of metaprogramming, because it improves developer happiness, it improves business people happiness because they get the stuff faster. Everyone's happy. Okay, here's another use case. So this is not meant to be read. I just wanted to show you the size of this thing. So this is the core logic of our delivery state code. Like how do the delivery objects transition from one state to another? This is like a state machine. So sometimes when you try to read this, it's actually very hard to understand what the hell is going on, because there's so many lines of code. Your computer has only so much height. Your screen has only so much width. Also, when you try to read things like when you try to read the text, it's not very easy to understand. So we're able to write a little bit of code, not more than like 100 lines, to be able to walk through the entire thing and build a graph of like what happens, how does a delivery go from like being created to all the way to being delivered. So this is actually very useful, because we're able to like generate this, print this on like a A1 size poster or like an A0 poster, and then we actually give it to like non-tech people, and they're able to like review if our logic covers like all use cases, whether the things are actually flowing the right ways. So essentially, we're able to get non-engineers to like do code reviews at some level. So that's another great use of writing programs that can read other programs. All right, so I've explained what metaprogramming is. Where do we go from here? So here are some ways of actually like doing this. Metaprogramming does not require a functional programming language. It simply just requires you to understand that the way you modify code is by using trees. So a lot of languages already have support for these concepts. So C# has this concept called expression trees. Expression trees. Who uses link in C#? C# link. Yeah. Okay. So C#'s link actually uses expression trees to transform C# code to SQL queries automatically. So if you're using that, you're already using some level of metaprogramming. F# has code quotations. Scala has quasi-codes. I'm sure Haskell has something. Lisp itself, the whole toolkit is metaprogramming. So if you're able to learn Lisp, Lisp is probably the most powerful language right now, because the kind of stuff you can do with Lisp macros, you can't do with anything else. So these are some interesting ways to explore this. Your language may already have a library. You can also write this library yourself. It's not difficult to write this, but very likely your language probably has a library. The way you check is just go to Google and type your language namespace, expression space trees, and something might pop up. Somebody might have been kind enough to like write a library and put it online. So, yep, that's it. Any questions?
Hi. Very interesting topic. Thank you. Since you're using metaprogramming, so can you use it for server-side rendering of native? Like if I'm coding, I'm doing a mobile app, I transfer the logics, and using this concept, can I actually render native GUI? Do you think?
You want to render native GUI on the server side?
No.
Sorry.
I'm passing information from server side.
Okay.
So based on that, I can create a GUI. Like if I pass a tree and based on that I create.
Yes, you can. You absolutely can. And we actually were doing this until we moved to React Native in our, so our premium apps, our previous apps were based on Xamarin. Don't use it. We had too much trouble with it. But all said and done, because the languages were the same between our front end and our back end, we were able to use C# expression trees. We actually serialize these expression trees and pass them on to the front end. So we were actually able to dynamically modify native code without any support from the underlying platform, and that's a very good use case for it. But if Apple ever finds out, you'll probably get blocked.
Could you build your own parse tree in the front end React Native and others, do they use the same technique or it's something else?
No, so React Native, I think just pushes JavaScript as a text. And since we have a full JavaScript execution engine on all the mobile devices, they don't use send parse trees, they just send the text over. The problem you have with sending full trees and executing them for everything in your mobile app is that the performance is not going to be 100% great, because nothing's better than actually compiling it to machine code and executing the machine code. So that's what happens when you build native apps. If you were to send parse trees over, you'll have to interpret them in using regular at your language level. So it's going to slow down things. So it's more useful for some parts of the application which you want to have more control over. Some small part of the application which you can't wait on an app update to happen. If you want to control the UI and you want there to be fine level of control, that I want that at design time you may not be able to think that I want these particular things. So that is the level of control you will get. Is that it? Okay, so if you want to, we have one more question? Okay.
Hi. So, how do you use metaprogramming in your front end? Can you tell us?
How do we use metaprogramming in our front end? So
libraries or techniques?
Right. So are you talking purely about front end or front end back end integration?
Only front end?
Only front end, okay. So let me just cover one small thing. Most of the time when you're writing front end in non-JavaScript, if you're using some kind of a transpiler, for example, CoffeeScript to JavaScript, or if you're using F# Fable to JavaScript, those are actually metaprogramming compilers. They're able to look at the parse tree and generate the necessary code. Without that, the same concepts which we discussed just now are actually transferable to the front end directly. So you can, there is nothing preventing you from, so the problem you have...
Let me rephrase. I was not talking about that. I was talking about the logics you were sending from backend to front end. How are you executing them?
I see, got it. Okay, so if you... Okay, this particular slide, so you see that we actually get this JavaScript, right? So you can just eval this. When you eval this, you will get one particular function. And the function parameters need to be fixed, unfortunately, because there is some contract you have to fulfill. This is the logic which you can control. So the backend sends this particular text to the front end. You end up evaluating it, you store the function against something, and you just supply standard parameters. It's just like a normal function call from JavaScript at that point.
I got it, thank you.